γιατί όπως ξέρετε οι ομιλίες μαγνητοσκοπούνται και μπορεί κανείς να τις δει στο κανάλι μας στο YouTube. So today's presentation is given by Orthodoxia, known as Sula Zervaki, and it is on the development and evaluation of collection techniques and direct reading methods for aerosol measurements. Orthodoxia received her first degree in chemical engineering at the University of Patras in 2016. And then she went to the United States, to the University of Cincinnati, where she obtained first her master's degree working on the calibration and evaluation of low-cost dust sensors. And then she proceeded with a doctoral degree at the same university, but working at the National Institute for Occupational Safety and Health of the CDCs, the Centers for Disease Control and Prevention. Her work at the time was on the design and development of new handheld portable aerosol collectors for integration with optical spectroscopies, aiming for low detection limits and high sensitivity. Then she continued as a postdoctoral researcher and further on as an associate service fellow at the National Institute for Occupational Safety and Health. The floor is yours, Sula.
Thank you. Thank you for the introduction, and thank you everyone for being here for my presentation. So I can start right away and with my presentation. Okay. First, I'm gonna start with an outline of what I'm gonna present to you today. I'm gonna start with, as you already mentioned, what I did for my master thesis, which was on the calibration and evaluation of low-cost dust sensors and monitors. I'm gonna present some key results for some sensor units that I have tested and evaluated. Then I'm gonna move on to my PhD dissertation. First, I'm gonna discuss the design and development of a multi-stage focusing nozzle for the effective concentration of a wide range of particle sizes into a small beam using a flow rate of 2 liters per minute, and for the collection of the aerosol sample on a small spot. Then the next study that I worked on was on the condensational aerosol growth using a mixing type condensation aerosol concentrator for the collection of the aerosol sample, either as a spot using a flow rate of 4 liters per minute, either as a liquid collection using a flow rate of up to 10 liters per minute. Then I'm going to discuss the evaluation of a laminar flow type condensation aerosol concentrator that was developed by Aerosol Devices. Then I'm going to discuss what I did for my postdoc, which was the co-development and evaluation of a TREAS, an instrument that uses both Raman and elemental spectroscopy for the more complete evaluation of the aerosol sample. And finally, I'm going to discuss the procedure for the development of a portable XRF method and the proposal for more simplified and cost-effective calibration standards that we can use for an instrument like that. So the first thing that I worked on for my master thesis was on the calibration and evaluation of low-cost dust sensors and monitors. This is the experimental setup that I used. I used a chamber which was approximately 1 meter tall, and it had a diameter of approximately 30 centimeters. At the top of the chamber, I had positioned the sensors, as you can see at the picture also. And at the bottom of the chamber, I had the reference instruments for the calibration and evaluation, which were the dust rack and an HHPC. These are some of the results that I obtained. I tested a big number of the same unit, of the same types and manufacturers, but here I'm going to present some results from one unit of each type that I tested. First, I wanted to see what was the effect, if any, of the aerosol chemical composition on the sensor's response. In the first case, we see that there is no impact, while in the second case, we see that when I used sodium chloride, the response I got was significantly different. And here I have some results post-calibration of some sensors. In the first case, we see a good agreement between the sensor and the reference instrument, except from, I would say, in the first case when cellulose was used, where the sensor could not detect the peak concentrations that the reference instrument could detect. In the second case, for the NOVA sensor, which was the only sensor that had active passing of the aerosol through the sensor with the operation of a fan, we see a good agreement between the sensor and the reference instrument, except from when the PM10 was provided from the sensor, where in some cases the sensor detected PM10 concentration higher than PM2.5, where before I started the experiments for this study, I did some measurements and I showed that we only have PM2.5 in the chamber. We didn't have any PM10. So the NOVA sensor erroneously gave me some PM10 concentration higher than PM2.5. But besides that, it was working just fine. And here are some monitors that I tested for this study. I tested the spec monitor and the Dylos monitor. The spec monitor includes a low-cost sensor like the ones that we saw before, while the Dylos monitor operates using the light scattering technique. I tested these monitors in two applications. The first was when I positioned the monitors in an office area where the number concentration was relatively low. And the second application was during the grilling of burgers in a residential area where the number concentrations are significantly higher. In the first application, we see that the spec monitor could not follow the reference instrument that well, in contrast to the Dylos monitor. While when we grilled burgers, we can see an increase in the sensor in the spec monitor's response as the number concentration increases. There is a slope, but the actual number concentration that is detected by the spec monitor is not the same as the reference instrument. For that reason, we can propose that to use the spec monitor mostly for qualitative measurements, while the Dylos monitor that operated way better, we can propose to use more for quantitative measurements. So generally, the key conclusions that I got from this study were that each unit, despite if we have a big number of units from the same type or the same manufacturer, we have to independently calibrate them. And then I also saw that the aerosol chemical composition may have an impact on some sensors. But collectively, we saw that we can use the low-cost sensors or monitors, especially in cases where bigger or more expensive instruments are harder to use. And then I'm going to move on to the next part of my presentation. But before I do that, I want to briefly discuss some different aerosol microconcentration techniques that are important to use, especially when we want to couple it with optical spectroscopies. The most common technique that is being used is the use of a converging nozzle. But in this case, we cannot effectively concentrate smaller particle sizes because of the inertia. And in most cases, we will have to use big bulky pumps to be able to handle big pressure drops. Another way to microconcentrate aerosols is the use of the aerodynamic lenses, where we can effectively concentrate smaller sizes too. But in this case, we definitely have to use big bulky pumps to handle the high pressure drop. Another way to microconcentrate is by using electrostatic collection, where we charge the particles and then we collect them on the surface of the opposite charge. This technique, though, it has a collection efficiency that is highly dependent on the size of the particle. And then we have noticed that we may have big losses during that collection. And finally, another technique that is widely used successfully is the condensation and aerosol growth technique, where we grow particles into droplets. We concentrate a wide range of particle sizes, even when we use high flow rates with a low pressure drop. So now I'm going to move on with the objectives, the key objectives of my PhD study, which were the development of new compact portable devices for effective collection of aerosols for subsequent analysis by optical spectroscopies with high sensitivity and low detection limits. Generally, we wanted to achieve 5 goals in this study. First, we wanted to be able to collect all particle sizes from nano up to micro size particles. We wanted to be able to use high aerosol sampling flow rates with minimum pressure drop. We wanted to collect the sample either as a small spot or as a liquid suspension. And finally, we wanted to achieve all this in a minimum space capacity. The first chapter of my study was about the design and development of a multi-stage focusing nozzle. This idea was based on a theoretical design that was proposed by Vidal de Miquel and Fernandez de la Mora, who proposed a design for a focusing concentrator that can operate with a laminar flow at very high Reynolds number. So the objective of this study was to design a multi-stage nozzle for collection of fine and coarse particle sizes, using inertia to collect them on a small spot. So this is what I did. I designed the multi-stage nozzle that is shown here, which is basically a sequence of smooth cavities that can effectively concentrate the particle trajectories into a small beam using a flow rate of 2 liters per minute. I tested this nozzle both numerically and experimentally, and I compared it with the conventional one-stage nozzle. Here is the simulation of the trajectories of 1 micrometer particle size through the multi-stage nozzle and the conventional one-stage nozzle. Here are the results from the numerical simulations where I compared those two nozzles. In the first case, we see the trajectories of 3 different particle sizes. In either case, I cannot collect 500 nanometer sized particles because of the inertia, but in bigger sizes, we can see that we can concentrate more effectively the particles when the multi-stage nozzle is used. At the bottom plot, we can see the spot that we can expect for different sizes of particles when I use the multi-stage nozzle or the one-stage nozzle, where we can see that in the first case we get a tighter spot that can enhance the sensitivity of the optical spectroscopy. This is the experimental transmission efficiency that I got. During the experiment, I noticed that we had a lot of losses through the nozzle that we did not expect through the numerical simulations. And this is probably because maybe we were not able to achieve laminar flow. Maybe the walls they were not as smooth as we wanted them to be. So there were probably some turbulence formed inside that were causing these losses. But anyways, I noticed that this transmission efficiency curve that I got was very similar to the PM2.5 fraction. So I decided to dig into this more and see when we can use this nozzle as a PM2.5 selective inlet. And in this plot, the contour plot, I show in which particle size distributions with specific geometric means or standard deviations, we can use this nozzle as a PM2.5 selective inlet with an acceptable bias. Here are the experimental, the collection efficiency that I saw experimentally of the multi-stage focusing nozzle in comparison to the numerical simulation, which is a relatively good match. And finally, I got the Raman intensity as a function of the mass density collected on the substrate. When I used the multi-stage nozzle, I got 4 different calibration curves for 4 different particle sizes because unfortunately Raman intensity depends on the particle size. And in every calibration curve, this is the equation that we get with the slope denoting the spectroscopic sensitivity indicator, which is completely independent of the collection method used. It's only dependent on the analytical method that is being used. And for that reason, we can take this equation, and by replacing the mass with this term, we can obtain a new equation, which is the intensity as a function of the aerosol concentration, where the slope is denoted by SC, which is the collection method sensitivity. In this way, depending on the collection method that we use, we can calculate the sensitivity of the measurement, and we can do a theoretical comparison. And this is what I did here. And we see that when the multi-stage nozzle is used, we can achieve higher sensitivity compared to other conventional aerosol collection techniques. And that concludes this study, where the multi-stage nozzle shows better performance compared to the conventional one-stage nozzle. We can achieve better sensitivity, and we can use this nozzle in a small portable instrumentation because of the fact that we can use a relatively high flow rate with a small pressure drop that can be handled by a personal sampling valve. So moving on to the next chapter of my study, something that we could not achieve before, which was the collection of all sizes. This is what we wanted to achieve moving forward. And I decided to start working with a condensational aerosol growth technique to achieve that. So I applied specifically the turbulent-mixing type of condensational aerosol growth technique using this setup that is shown here. Here I show the inside of this setup to give a brief description of how it works. This device consists of 4 key compartments. First, we have the saturator. The saturator is basically a water container that has an immersion heater at the bottom and a temperature sensor at the top. Inside the water container, we have a Nephion tube That is a membrane that is only permeable to water molecules. At the entrance, we have a particle-free air coming in at room temperature, and at the exit, we have a water vapor saturated flow at the temperature, the same temperature as the water that is being heated inside the container. This water vapor then enters the mixing section, which is a T-shaped mixing section where at the top we have the entrance of the aerosol flow, which is at ambient temperature. And we have a theoretically instant adiabatic mixing of these two streams that causes generation of supersaturation, where the water vapor goes and condenses on the surface of the particulates. And then we have the droplet formation and the growth that is further enhanced during the growth tube, where more time and space is given for the mixed flow and the droplet growth to happen. And then at the outlet, we have a converging nozzle that concentrates the beam into a small, concentrates the mixture into a small beam for subsequent collection of the sample on a heated substrate where the water evaporates, leaving behind the dry aerosol sample. Some applications of this device are Raman spectroscopy or scanning electron microscopy, and transmission electron microscopy, IR, etc. Anything that requires a sample to be concentrating on a substrate, any type of substrate. And these are some results that I got from the characterization of this setup. First, I wanted to see what is the optimum vapor to aerosol flow rate that I have to use. Each subplot here is for a different temperature of the water that was being used. The water was being heated up to 70, 75, 80, 85 degrees of Celsius. The solid line represents the calculated saturation ratio, which in all cases, it was above 1, that showed that we can expect activation and further growth of the droplets. Now, another thing that we notice, the dashed line and the points represent the experimental activation efficiency of 25 nanometer particles up to sizes greater than 1.4 micrometers. In all cases, we see that we have at least some partial activation growth, like in the first case at 70 degrees of Celsius. In higher water temperatures, we can achieve complete activation efficiency. Now, another thing that we notice here is that as the temperature of the water increases, the optimum water hot vapor to aerosol flow rate decreases. For example, in the first case, the optimum ratio is at approximately 0.25, while in the last case, the optimum ratio it's at approximately 0.15. So at the following experiments for the further characterization of the setup, I used a different flow rate ratio for the optimum operation. The next thing that I tested was the activation efficiency as a function of the aerodynamic diameter of the C aerosol that acted as a nuclei. And I saw that in most cases at water temperatures of 75 degrees of Celsius and higher, we can get nearly complete activation down to 25 nanometers. The optimum inlet relative humidity range that is recommended for this setup was in the range of 25 to 100% for the aerosol flow. Another thing that I wanted to test was the performance, the operation of the setup at long times. to see if we have any heat transfer between the compartments that could affect the operation of the setup. I ran it for 60 minutes. I didn't see any difference. So I would expect it to run just fine even for longer times. And finally, another thing that I saw was the effect of the number concentration on the activation efficiency, where as the number concentration increases, we have more particles that droplets form and grow around them. This change in phase releases heat, and we should expect an increase in the temperature of the mixture, and that could lead to a deterioration of the performance, which we notice happening at approximately 35,000 particles per cubic centimeter. Another thing that I tested was what was the position area that we can obtain for different particulate sizes. I used PSL spheres from 20 nanometers up to 2000 nanometers, and I got the same deposition area for all of them, approximately 1.4 millimeter diameter. And finally, I calculated the same way as I did before, the measurement sensitivity of this collection technique in comparison with other conventional collection techniques. And we can see that we can obtain a better sensitivity when we use the spot sample TCAC. And finally, I did some calculations there is a NIOS method specifically for fiber counting when we use phase contrast microscopy. Specifically, how we do that? We collect first the sample on a 25 mm diameter filter. Then we take the sample, we put it under the microscope. We zoom in an area of 0.785 square millimeters, and we count manually the fibers that we see on them. So the method proposes an optimum fiber density of 100 to 1300 fibers per square millimeter to achieve a counting uncertainty between 3 to 10%. So if we assume a concentration of fibers in the air of 0.1 fibers per cubic centimeter, I was able to calculate what was the sampling time that was required when we used the spot sampling TCAC in comparison to the sequential spot sampler or the 25 millimeter filter. We see that we can get way lower sampling times compared to the 25 mm filter, and slightly lower compared to the sequential spot sampler. So the next study that I worked on had to do with an upgrade of this device. We wanted to achieve higher flow rates. In the previous device, we were working on 4 liters per minute. Now, when you collect droplets on a substrate that you have to heat, you can increase the flow rate, but you will have to increase the temperature of the heated substrate to be able to evaporate the water as quickly as you collect the droplets. And for that reason, because it was getting too complicated, we decided to switch to liquid collection so we can increase the flow rate without having any concerns on that. And this is what we did. We went up to 10 liters per minute collection flow rate, and I increased the size of the mixing section a little bit and the size of the growth tube as well. And I also replaced the plastic growth tube that I was using before with an aluminum one. And I put 2 thermoelectric coolers on two opposite sides of the growth tube, so I can cool the whole growth tube, and with the aim of enhancing the growth tube of the droplets. the growth efficiency of the droplets. After the growth tube, we have the converging nozzle that again concentrates the droplets into a small beam, which then impact on an inclined surface, sliding on it, and then there was a hole at the bottom of the surface where the droplets were flowing through, concentrating at the bottom of this collection vial, which at the end of the collection you can just remove and you can analyze with any technique that requires for the sample to be in a liquid suspension, like ICP AES, ion chromatography, and others. I did the same characterization as before. I saw that I was able to collect particle sizes down to 25 nanometers effectively. I tested it for 3 different flow rates, 8, 9, and 10 liters per minute. I was able to, the optimum temperature of water was different for each flow rate. The growth tube temperature was at 0 degrees of Celsius at all time, because this is where we were getting the best results. And I also found the optimum RH range for the aerosol flow rate for each aerosol flow rate that I used it for. And these are some extra results when I tested the number concentration effect on the collection efficiency. We can get a complete collection up to 300,000 particles per cubic centimeter, which collection efficiency starts dropping at higher number concentrations, and it reaches 50% at the number concentration of 1 million particles per cubic centimeter. And the next plot that shows the mass recovery, it was obtained by doing the following experiment. I had one line where the liquid sample TCAC was collecting sample at 10 liters per minute. And in parallel, I had a filter, a 37 mm particulate filter collecting the same sample at 10 liters per minute. So in the x-axis is the mass that was collected on the filter. And on the y-axis is the mass that was collected on the liquid sampler. This mass was first extracted on a filter through vacuum filtration, and then I used the mass balance to obtain the weight of it. And this is the correlation of these two techniques. We see a perfect agreement between the two techniques that show that we can use the liquid sampler the same way as we use the filter when we need to collect the sample in a liquid suspension. And this is the prototype that was developed by Aerosol devices that obtained this technology. And it uses this collection technique that I just described. And we have some plans on this. One of the things that I want to test it for, you can use this for collecting pretty much anything in the particulate phase. I want to definitely evaluate this collector specifically for bioaerosols, which is something that is needed in this area. And now I'm gonna move on to the next and final chapter of my PhD, which is the evaluation of the Nanospot collector that was developed again by the Aerosol devices. The Nanospot collector uses an aerosol flow rate of 1.2 liters per minute. And this is the schematic of the operation of the Nanospot collector. First, we have the aerosol flowing through 3 different stages. First, it flows through a cold stage, the conditioner, which cools the aerosol flow and humidifies it. Then it flows through the initiator stage, where the wick that surrounds the aerosol is heated at high temperatures, releasing vapor across the radial axis of the aerosol stream. And then because the vapor diffuses faster across the radial axis than heat does, we have generation of supersaturation, and the same growth, vapor activation on the surface of the particulates and subsequent droplet growth. The mixed stream subsequently flows through, and again, cold states, where the growth of the droplets is enhanced before it gets concentrated into a small bin through a converging nozzle, and it gently impacts on the warm surface of an SEM stub or a TEM grid holder. This way we can collect the sample directly on a surface that is required specifically for these analytical procedures without having to deal with handling of the sample, transferring, having losses through these processes. And this collector works pretty much the same way as a sequential spot sampler does. The only difference is that instead of one long growth tube that the sequential spot sampler has, we have three shorter ones that minimizes the size significantly of the collector and the weight as well. And here are some theoretical calculations that I did on it. This is the first we see the calculated saturation ratio across the length of the growth of each growth tubes in the Nanospot collector for two different initiator temperatures. In both cases, we see that we can get a saturation ratio greater than 1, which is required for activation and growth to happen. In the second plot, we can theoretically calculate the size of the droplets across the length of each of the growth tubes. And we see that in all cases, the smallest droplet size that we will get at the exit of the growth tube is going to be greater than 3 micrometers, very easily collectible. Then I have the experimental collection efficiency as a function of the particle size. And we see that no matter the type of aerosol used, we can get a great collection efficiency down to sizes of 5 nanometers. Then I have the number concentration effect like before, where we see the collection efficiency at different conditions as a function of the number concentration. And again, I got the spot deposition area for different PSL sphere sizes from 20 nanometers up to 2000 nanometers. We get a similar deposition area no matter the initial particulate size. And again, like before, I was able to calculate theoretically the sensitivity that we can get when we use the Nanospot collector, which is better than the other conventional aerosol techniques that we generally use. And now I'm gonna move on to some stuff that I did for my postdoc. First, it was the co-development and evaluation of TREAS, which is the tandem, random, and elemental aerosol spectrometer. Here, this scheme shows the heart of this instrument, where the collection and the analysis of the aerosol happens. First, we have a simple converging nozzle that concentrates the aerosol sample on the flat surface of an electrode. After the collection is completed, the electrode rotates by 90 degrees, where it faces a Raman probe. After the Raman spectra are acquired, then the electrode rotates again by another 90 degrees, where the sample now faces a sharp electrode. The sharp electrode and the collection electrode, they form, when you apply high voltage, you have a spark generation that's burning the sample, and the radiation that is emitted is then being collected by an optical fiber cable, which can give you elemental identification of the composition of the sample. This also ablates the whole sample. It cleans the collection electrode, and then it's ready to return to its initial position, where the new cycle of collect, analyze, and ablation begins. These are some results that we got during its evaluation. That also show the importance of having both analytical techniques into one instrument. First, we used it to identify and quantify some compounds of interest for NIOS, which are the silica and the titanium dioxide. We used two different engineered stones and fracking sand dust. In the first case, we see the two characteristic peaks. The red lines are the Raman spectra, and the blue lines are the spark-emission spectra. So in the first case, using the Raman spectra, we see the two characteristic peaks that we get when we have the titanium dioxide. We also see the titania in spark-emission spectroscopy, along with some other elements. Something else that we see in the elemental identification is silicon, which we do not see in Raman, and this is probably because we expect this peak at 465, and it's probably covered by the presence of titanium dioxide. This shows why we need both measurements, where one technique can see one compound that the other cannot see for any reason. In the next two cases, we see only crystalline silica, which is alpha quartz, that we can see through Raman spectroscopy. And then again, using spark-emission spectroscopy, we can see the element as well. And then in the fracking sand dust, is it again the same situation? We can see after peak deconvolution the alpha quartz peak. In either case, we could see titanium dioxide, either engineered stone B or fracking sand dust. Below, we see the limit of detections that were calculated for alpha quartz and titanium dioxide using either Raman or spark-emission spectroscopy. And here are some other applications where both techniques are required. First, we have the testing of some carbonaceous aerosols. When we apply Raman spectroscopy, we get the two characteristic peaks, the D and G peaks that we expect for the carbonaceous aerosols in all cases, like black carbon, multi-wall carbon nanotubes, and diesel particulate matter. But when we apply spark-emission spectroscopy, we cannot see carbon because it's outside of the detected range of the specific spectrometer. But we can see the presence of other elements, particularly in the case of diesel particulate matter, which has a lot more elements than carbon. And finally, another thing that we can we can use this instrument for is for the identification of different oxidation states. For example, when we have a welding fume sample, particularly the specific case where the unknown sample is it's a stainless steel welding fume, and in case we want to see for the chromium, for example, specifically, chromium-6 is way more toxic and more carcinogenic compared to chromium-3. It has different exposure recommended and permissible exposure limits, and it's of high significance to be able to detect specifically chromium-6. When we use spark-emission spectroscopy that sees only the elements, we cannot differentiate. We can see the chromium in all cases, but we cannot identify the oxidation state. But when we do Raman analysis, for example, in the top 3 subplots for the Raman analysis, in the first case, I have the Raman spectrum that we expect to see when we have chromium oxide. And then I have the Raman spectrum that we expect to see when we have chromite or chromate. In the first case, the chromium is in oxidation state 3. In the second, it's in oxidation state 6. So when we have the stainless steel welding hue sample at the last subplot, we want to see what oxidation states we have. We can say with high certainty that it's most likely not chromium 6 because we do not see the peak that we would expect to see, which is at approximately 850. And most likely we have chromium 3, which is probably buried under this peak here that was obtained through deconvolution at approximately 700. So these all show some different applications where this instrument can be used. And now I'm gonna move on to the last part of this presentation, which is, it was part of a method that we wanted to develop that had to do with the direct reading of metal and metal oxides on the field by using a portable handheld XRF analyzer, specifically for welding fume samples. Basically, what we wanted to achieve was for, let's say, there is a welder on the field doing their shift. They use a personal sampler where the aerosol sample is collected on a 37 mm filter. And after the 8-hour shift, for example, we can get the filter. And right then and there, we use a handheld XRF analyzer to quantify and specify the elements, the metals that exist, that the welder is exposed to. And we get the results right then and there with no sample preparation, without having to wait for days to get the result. So we can get instant and fast decisions. A problem that exists with this is that the calibration standards that are generally used for techniques like that are either very expensive, in the order of thousands of dollars, or the preparation for these calibration standards, it's very complicated. Like some labs, maybe they don't have access to a mass balance, or they don't have access to setups like vacuum filtration, so it's not easy for them to prepare calibration standards. So what we wanted to do here was to propose some simplified and cost-effective methods to prepare your own calibration standards. And how I did that, you can obtain from the market some very highly concentrated, certified reference material solutions that contain pure metal salts. You can get this for maybe $90 per sample. And you can create your own serial dilutions by using just one pipette. Very simple preparation procedure. And then you take a filter, any filter that you want to use as your substrate. I use the MC particulate filters because they are being widely used, particularly for metal detection. And I spike 3 microliters of all my solutions on the center of the filter. The key on this preparation technique is that the spike sample has to be smaller than the X-ray beam that is analyzing the sample. This way, we don't care about the deposition area. We don't care if the sample is uniformly deposited or what is the exact deposition area of the sample. And also another advantage of this is that, as we know, the presence of different metals can have some interference on the detection on specific metals. So you can prepare filters that either contain one metal, or they can also contain multiple metals in different compositions. So you can take into account this interference into the calibration, so you wouldn't have any unexpected issues later when you want to quantify the unknown sample. So this is what I tested. These are some Plant-Hallman plots that show the percent difference of a handheld XRF analyzer compared to the established NIOS method that uses ICP-AS for the detection of metals. In the first column, I have the quantification when single element calibration curves were used, while in the second column I have the quantification when multi-element calibration curves are used. And as it was expected, in the second case, we get way better results, way better agreement between the two analytical techniques, just because the interferences are not a problem anymore when we have multi-element calibration curves. And finally, this is a plot that shows the recommended and permissible exposure limits that were established by OSA and NIOS in comparison to the calculated limit of detections for the handheld XRF and the established NIOS method that uses the ICP-AS. In most of the metals, we see that we can successfully detect with any analytical method we use, we can successfully detect the exposure limits, except from chromium, specifically the case of chromium-6, the recommended exposure limit of chromium-6 cannot be detected when we use the handheld XRF, while the short-term exposure limit of chromium-6 cannot be detected from either handheld XRF or ICP-AS either. And also in the case of arsenic, the recommended exposure limit cannot be detected by either techniques. Other than that, we can definitely use the handheld XRF in the place of the benchtop ICP-AS, which requires preparation of samples and very time-consuming procedures for the analysis of the samples. And that concludes my presentation. Thank you, everybody, for being here, and any questions you have, feel free to ask.
Thank you very much for a very detailed and enlightening presentation. Your presentation now is open for questions and comments.
Yes. Hello, Yanni. May I open the floor for the questions?
Please, but I think, yes, Dimitris wanted to ask something.
Sorry. I don't see the participants. Sorry, of course, Dimitris first.
Is that correct? Maybe not. Go ahead, Georgia.
Okay, so Orthodoxia, congratulations for the very nice, very interesting results, and a lot, let's say, in quantity. There, you cover a wide range of measuring techniques and applications, so congratulations once again. I would like to ask some technical details for your Raman measurements. First of all, what was the wave number of your Raman instrument? Are you aware?
It was the laser, it was at 780 nanometers. This was the laser probe that we had, yeah.
Okay, so may I ask, didn't you have any fluorescent? Usually you have an offset when you have a fluorescent in your samples, or you did not detect did not detect any fluorescent in your measurements?
I did detect fluorescence, but all the results that are shown here are corrected for the baseline.
Mm-hmm.
So basically, I was bringing everything down by correcting for the baseline, yes.
Okay, so this but in principle you believe that but also by this correction you can also take into consideration you can adjust all those measurements for having this comparison that you showed in your spot sample TCAC, where you said that the intensity of your measurement may be in correlation with the concentration of your sample, correct?
Are you referring to the one with the different particle sizes?
Yes.
Okay, let me go there. Can you repeat your question?
Yes. So, yes, in this sensitivity indicator, you mentioned that the intensity of the Raman signal can be correlated to the concentration of your sample or to the size. You said size of your sample.
Yes. Yes. So this is an intrinsic problem that Raman has. Generally, we just take any particle size distribution we have, we collect different masses, and we get the calibration curve. I think because it depends on the particle size that you have, this should always be accompanied to the particle size distribution that you have every time. Here, because I was able to, to control the different sizes that I wanted to get and everything, I was able to get different calibration curves for different sizes. But when you have like an aerosol sample outside in the ambient air, you might have some differentiations from your calibration curve, especially if you have a different peak size. This is something that you cannot avoid, unfortunately. There are some, I'm not sure if there are. This was something that my previous team was working on. They wanted to find ways to maybe apply some correction factors for that. But generally, when you, I don't know if, I think the results wouldn't be that different. Maybe there will be some minor differences, but especially when you have like a big mass on your sample, I don't think the size would cause any big differences. If you have one main calibration curve, I think you can get a good estimate of the mass that you have. But yeah, this is something that my team was working on to see what the different size effects are and how we can overcome this for identifying, quantifying an unknown sample. But for the scope of this study, it was outside of this. Yeah, but thank you for your question.
No, thank you for the answer. Thank you very much. And again, congratulations.
Thank you. Thanks.
Any further questions? I presume your presentation was very clear and to the point that the audience has no further questions. So I would like to thank you once again. And this concludes today's presentation. I would like to remind you that the hard YouTube channel is fully functional, and you might find previous talks there, which you can listen at your leisure. I would like to wish you all a good evening and looking forward to seeing you to our next meeting, next seminar, which I presume will be, one second, I think it would be I don't remember, towards the 21st of January. Have a good evening.
Have a good evening. Bye.
Γεια σας.
Γεια σας όλους. Καλό βράδυ.